Hello and welcome to the Ways of Math. I'm your host, Dan the Math Man. And today we're going to continue our series on the introduction to sets. So this is part 6 of this multi-part series. And in this video we will describe the meaning of the words and, or, and not specifically in regards to sets, and we will formalize using these. So we want to be precise when we use the word and, or, and not. We want to be very careful because they do translate to mathematical, or at least we commonly accept the usage of the words and, or, and not to translate formally mathematical concepts in regards to sets. Okay, so we're going to formalize the usage of and, or, and not in this video. We'll also produce a formula for the cardinality of the regions of two sets, and then we will come up with an example. So we will see an example that uses this formula. Okay. So hopefully we've begun to see that when we're discussing sets and using the terminology of or and, these are roughly translated to mean the union and the intersection of sets respectively. So if I talk about elements in one set or another set, we're actually talking about the union of the two sets. Or if we talk about elements in one set and another set, we're actually talking about the intersection of these sets. Okay, and then the usage of the term not, so usage of the word not, translates to the complement of a set. So not in B or not in A, so not in a set simply means that we're in the complement of the set. In fact, if we recall the way we formally write union, intersection, and complement of sets, we actually see these very words in the definition, and this is why we are allowed to formally use these. So recall, the union, A union B, is the set of elements X such that X is an element of A or X is an element of B. All right, so we see the word or explicitly used in the formal definition of union. Intersection, A intersect B is defined to be the set of X value or values of elements X such that X is an element of A and X is an element of B. Okay, and the complement, right? So recall we define the complement of a set A as being the union subtract or the universal set, sorry, subtract the set A, right? So the universal set minus A. Now, recall how we defined this subtraction, okay, as the set of elements X such that X is an element of the universal set and X is not, that's what that symbol is read, an element of A, right? So to be in the complement, we are in the universal set. Of course, we have to be in the universal set, and we are not in A. So to be in the complement means to not be in A. Okay? So in fact, if we say an element is in a set A or B, we are in fact saying that is an element of A union B. If we say that an element is in the set A and B, or the sets A and B, we are saying that it is an element of the intersection of A intersect B. Okay, and so notably these are kind of interchanged kind of informally, so we can say A union B, but now that we formalize this, we can also say A or B, right? So A union B is equivalent to say that we're in the set A or B, and to say A intersect B is equivalent to say in the set A and B. And then if we say an element is not in the set A, then we are saying that it is an element of the complement of A. So to say that we're not in A is to say that we're in the complement of A. Or if we see A complement, we can say not in A. Okay. Hopefully, this allows you to more understand or more fully understand the concepts of unions, intersections, and complements. Right. So now we have a more convenient way of talking about unions and intersections and complements. Okay. Now there's another important relationship to know, and this deals with the cardinalities of sets. Okay. And so this brings us to a theorem. The cardinality of the union of two sets, A and B, is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A. So here, when we talk about plus and minus, we're not talking about set, well, set addition isn't defined, but set minus, set subtraction. We're not talking about subtracting sets. Remember, the cardinality is a number. So the cardinality of A is a number, so we add to it the cardinality of B, which is a number, and then we subtract the cardinality of the intersection of A and B. Okay, so we're just adding up integers there. And then formally, we can write the formula, the number of elements in A or B, so A union B. So this is, remember, N is the cardinality. The number of elements of, or the cardinality of the union, is equal to the sum of the cardinality of A and the cardinality of B minus the cardinality of the intersection A and B. Okay, and then we can see this more obviously in a Venn diagram, right? We saw in the last video the illustrative powers of the Venn diagram to help us kind of visualize a lot of these things with sets. So the cardinality of A union B is the number of elements that are either in A or in B, right? And this encompassing this is the light blue, the purple, and the pink regions, right? So regions 1, 2, and 3 is A union B. Okay, so we can add, right? So the cardinality of A will be the number of elements contained in the blue ellipse, right? So everything contained in the blue ellipse, which is regions 1 and 2, is the cardinality of A, and the cardinality of B is everything in the red ellipse, which is in regions 2 and 3. Okay, and now if we add these up, notice we're adding region 1 and 2 to the regions 2 and 3. So we added 2 twice, right? So if I add the number of elements in A to the number of elements in B, we double counted this region 2. Because we count, these elements are in both A and B, so we counted them twice. And so that's actually why we need to subtract that extra region, that's this purple region that got counted twice. Because remember, these are all disjoint. So I can add up region 1 plus region 2 plus region 3. But if I don't have necessarily the Venn diagram, or maybe I don't have explicit sets that are easy to define broken down by elements, then it might not be easy to add up region 1, region 2, and region 3, or to find the cardinality, add up the cardinalities of region 1, region 2, and region 3. So we might want to add just the cardinality of A. It might be easier to know what the cardinality of A is, and then the cardinality of B, but then realize that we might have double counted, or if there is such a thing, we would have double counted as region 2. And that's why we subtract off that double counted region 2. Okay? So let's take a look at an example of how to use this formula. Suppose we survey our neighbors and ask if they have network cable, a streaming service, or both. Results were that of the people sampled, 8 of them had cable service, 10 of them had streaming service, and 5 of them had both. How many people did we survey? Now, be careful to avoid the temptation that assuming that all these people are different, right? We're saying that 8 of the people surveyed had cable service, 10 of the people surveyed had streaming service, and 5 of the people surveyed had both. Okay, so clearly those that had both were counted in the people that had cable service, right? If they have both, then they have cable service. If they have both, then they have streaming service. So we've actually counted some people multiple times. So we want to avoid the tendency to just go, oh, the number of people surveyed is just 8 plus 10 plus 5. Okay, so we're going to use our sets and what we know about sets and this new formula that we have in order to formalize this, because we want to know how many people, individual people, do we survey. So let A be the set of neighbors with the cable, and let B be the set of neighbors with a streaming service. Then the cardinality of A is 8, right? And the cardinality of B is 10. Then, and also the cardinality of the intersection A and B is 5, right? So there are 8 people that had, of the total people that we surveyed, 8 had cable. So that's why the cardinality of those that had cable is 8. And the number of people surveyed of those, B, the cardinality of B, which is 10, are those that had the streaming service. And then the cardinality of the intersection are those that had both. So 5 of them had both. Okay. And by the formula, if I want to know how many total people were surveyed, right? It's the number of people who had either cable or streaming service. Okay. So one or the other. And this will give us the total number of people surveyed that had these. Then the number of A union B is equal to the number of A plus the number of B minus the number of A intersect B. That was our formula. And so now we just substitute our values. So the cardinality of A, the number of elements in A, is 8. The number of elements in B is 10. The number of elements in the intersection A and B is 5. 8 plus 10 minus 5 gives us 13. So we surveyed 13 people. Okay? So of those 13, right, 8 of those 13 had cable, 10 of those 13 had streaming service, and 5 of those people had both. Okay? So we see in this example, right, it going back to our Venn diagram, it would have been hard to separate each individual neighbor into these categories because we don't know who the neighbors were necessarily, right, at least in the problem. So we couldn't have constructed a Venn diagram to illustrate this. All we knew were the number of elements in the sets, and so that's why we had to rely on the formula and the cardinalities of the sets in order to solve our problem. Okay? Well, I hope you enjoyed this video. Thanks for watching. Please be sure to subscribe to the channel and get notified of any future videos. And please leave any comments or suggestions in the comment box below. I thank you for watching. Have a wonderful math-filled